Okay, so when we're looking at the hybridization of C double bond O, carbon dioxide, we've got two sets of lone pairs on each oxygen. So the first thing that I'm going to look at is the types of bonds. I have a sigma bond is always the first type of bond in a double bond, and the second type of is a pi bond in the double bond. So now I have those arranged. Just based off of first glance, the carbon has basically two zones of electrons around it. If it's two zones, usually that becomes an sp because it's 2 minus 1. And the oxygen has these lone pairs on either sides. So we've got 1, 2, 3 zones around each of the oxygens. So I would predict these are going to be an sp2, 3 minus 1 sp2. We can prove that with the orbital diagram. So I've got the neutral orbital diagram for a carbon atom. I know that a carbon atom has 6 electrons, so I'm going to draw these in here. 1, 2, 3, 4, 5, 6, distributing them evenly in that neutral 2p orbital. So that's for a neutral carbon. So what this means is that that carbon is going to form two pi's and 2 sigma bonds. So that means in order for it to form 2 pi bonds, I need to reserve 2 of the last p orbitals for those pi bonds. So these ones are going to go towards forming the pi bonds. I also need to form 2 sigma bonds. So that means that these 2 are going to be reserved for promoting the sigma bonds or forming the sigma bonds. So when I mix these and hybridize them together, I'm left with a 1s. The 2s and 1 of the p orbitals are now hybridized together. So this was an s, this was a p, and then I'm also left with 2 p orbitals that are reserved for the pi bonds. So nothing's going to happen with the 1s that's untouched, but the s and the p, this becomes sp hybridized, and those are for the sigma bonds, the 2 sigma bonds that form. So 2 electrons are in there, can form sigma bonds. Then we also have the p orbitals that have 2 electrons in there. 1, 2, 3, 4, 5, 6 electrons total. So we've distributed them. The top p orbitals can form the pi bonds. So now when we introduce the oxygen into this diagram, I'll put 1 oxygen above. If we draw the neutral oxygen, we have 1s, 2s, 1, 2, 3, 2p. So neutral oxygen has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So the oxygens are forming, we can see 1 sigma bond to the oxygen, 1 pi bond, and 2 lone pairs. So I'm going to take 1 of the orbitals and say that is going to be reserved for a pi bond. 1 of the orbitals, or 1 of the electrons, needs to be reserved for the sigma bond. And that leaves 2 left that go towards lone pairs. So we'll say these 2 are going to go towards the lone pairs. And that makes sense because those ones are already paired up. So then when we hybridize these orbitals, we now have our 1s again, and the 2s and 1 of the p orbitals are hybridized together. So that's how we get this sp. However, we need to include only 1 pi bond at the top. So there's only 1 pi bond unaccounted for at the top, which means this sigma bond actually goes and becomes included in the p-sp orientation. So that's how this becomes sp2, because only 1 p orbital has to be reserved at the top because there's only 1 pi bond being created, as opposed to the carbon, we had 2 pi bonds being created, so we had to reserve 2 at the top. So that's how we get the oxygen hybridization of sp2. Now we can fill in our lone pairs or electrons again. 1, 2, 3, 4, 5, 6, 7, 8. And that works out so perfectly because we can see our 2 lone pairs are accounted for here. There's 1 electron that's going to go towards the sigma and 1 electron that's going to go towards the pi bond. So really what that means is that pi bond electron is going to bond with one of the electrons in our carbon. So it's going to go there. Then we also have the sigma bond is going to form a sigma bond with the carbon, and we can input that one here. Well, now we have still 2 unbonded electrons in that carbon. However, we know that there's 2 oxygens. So basically everything that we've drawn for the first oxygen can be redrawn for the second oxygen. I have a 1s, I have a 2s, 1, 2, 3, I have a 2p. This is my neutral oxygen. I put in my electrons, 1, 2, here, here, here. And again, the same thing, I have lone pairs. So these ones are going to be for lone pairs. I need to designate 1 electron to form that sigma bond and 1 electron to form the pi bond. So when I hybridize these orbitals now, the 1s stays the same. The 2s, I've got an s and a p orbital, but also that sigma bond is included here, so that one is going to be the last p. And the pi bond is basically designated at the top. So the top one is for the pi bond, and the second one is for the sigma bond. However, we know we have these ones will be lone pairs because we have 2 sets of lone pairs on each of those oxygens. So that means where are these the 2 bonded electrons coming from? Coming from this second oxygen. So to fulfill my pi bonds, I'm going to match the pi bonds together, and then I'm also going to match the sigma bonds together right there. And that is how our carbon becomes fully bonded.